Assalamualaikum and hi everyone. Welcome to my class, Computational Mathematics. I will be teaching in section 03 and 07. So, for today, we will start with chapter 1, which is System of Linear Equations and Matrices. Okay, as you see in chapter 1, we have 3, 6, 7 things that we need to cover. And I have divided in two for week 1 and week 2. So for week 1, we will have system of linear equations, matrices determinants, and matrix inverses. And next week, we will go into elementary row operations, the Gaussian elimination, Gauss-Jordan, and also matrix factorization, Doolittle and Crouch. We start with linear equations. This is the form of linear equations, as you can see in the first line here. X in linear equation is a variables. A is real numbers and can be called as the coefficients of the variables. The number B is called the constant term of the equations. Okay, this is a column of matrix. I think you are familiar with matrix already. Alright, this is the matrix of variables. In linear equations, we have a set of numbers represented by S. It is called a solution to the linear equation if this condition is met, whereby values of S are substituted for the variables X. For example, this question asks us to show that whether these matrices X equal to 1, negative 2 transpose is a solution to the equation 2x1 minus 3x2 equals to 8. But these matrices Y equals to 1 and 1 transpose is not a solution. We can show that these matrices X equal to 1, negative 2 is a solution by inserting directly x1 equals to 1, x2 equals to negative 2 into the equations. When you do this, you will get the same thing. Okay, so it satisfies the equation because it is the same. But for x equal to 1 and x2 equal to 1 also, when you put it inside here, it will not be equals to 8. So this matrices is not a solution. Another example here asks us to determine whether the points of negative 1 and 5 and 0, negative 2 is a solution to the given system of equations. Okay, they give us 2 here. Y equals to 3x minus 2, y equals to negative x minus 6. Okay, again, to answer this, you need to plug the x and y coordinates into the equation and check if they work. First, we check negative 1, negative 5. So, y is negative 5, x is negative 1. When we do the solutions, it checks. It is the same, negative 5 and negative 5. But we also must check another one. We have two system of equations. So again, this is y, this is x. And then when we do the calculations, it is the same. So the solution checks. Since the given point works in both this one and this one, it is a solution to the system. Now we look into the second one, 0 and negative 2. As you can see, for the y, it is negative 2. For the x, it is 0. For the first one, it checks. It's the same. But for the second one, when you do the calculations, it is not the same. -2 equals to -6, so it's not the same. Therefore, only the point, the previous one, -1 and -5, is a solution to the system, because 0 and -2 only satisfy this one, not the second equations. What is system of linear equations? It is a finite collection of linear equations, and it is a system of m equations in n variables. The system has a solution if there exist a numbers S that can satisfy the equation simultaneously. The system is called consistent if it has one or more solutions. If one, we call it unique. If more, we call it infinite solutions. The system is called inconsistent if it has no solution. So we have three options here. This one, unique, infinite, both are consistent, and no solutions, it is inconsistent. We go to the first one, unique solution. For example, here they give you a system that has 1x plus 1y equals to 4 and 2x minus 3y equals to 6. When you plot this into the graph, you will have this type of lines. We have two lines here. This line is for the first one, which is this one. This is the second line for this system. Okay, how we get this line? Alright, if you put y is 0, x equals to 4, so this is x. If we put x is 0, y equals to 4, this is y. So this is the line. Okay, this is the line. For this one, if you put x and y is 0, 2 brought down here, so it will be x equals to 3. So x equals to 3. And then if you put x is 0, this one is -3. Sorry. So it will be -2, which is this one. If you plot the line, you will get this is the one that it will intercept each other. Okay. The point where the line cross, this is the number. It is where it is crossed. 3.6 is x, y is 0.4. Is the solution that satisfies both equations simultaneously. So when it crosses just one line here, one plot here, so the solution is unique, and if it is unique, it is consistent. Another example asks us to show whether it has solution of x1 equals to 2 and x2 equals to 3. Okay. You insert the x1 with 2 and the x2 with 3. Is it satisfy 5? So for this case, the first one, yes. 2 plus 3 equals to 5. 5 equals to 5. For the second one, if you put x1 2, x2 3, 3 multiplied by 2, got 6, plus 2 multiplied by 3, we got 6, and it is also equals to 12. So the two lines are not parallel and intersects at point 2, 3, because these 2, 3 satisfies both equations. So it is consistent. Okay, now we go to the second one, infinite with many solutions. They give us two systems, 1x plus 1y equals to 4 and 2x plus 2y equals to 8. If we plot this to the graph, we will have both lines, both of them are the same. Because yes, if you put 0 here, of course, x will be 4. If you put x 0 here, y will be 4. So this one, same line. If you put here y is 0, x we divide it by 2, so it become 4 as well. X also the same. If you put 0 for x, y also will become 4. So both lines here intercepts along these lines. So it is a redundant system with infinite number of solutions. The system is redundant because second equation is equivalent, same to the first one. They crossed at an infinite number of points. So there are infinite number of solutions and it is consistent. This is another example of infinite solutions. We have two systems, two linear equations here. x1 plus 2x3 equals to 6 and x2 plus x3 equals to 2. These have many solutions whereby t is arbitrary. We insert t into the equation. Arbitrary means can be any number and still satisfies this equation. So how to insert t here? We start with x3. We change x3 to t. So x2 is equal to, we move it to here, 2 minus t. And remember, x3 is t. So we insert t into this equation. x1 is equal to 6 minus 2t. Okay. Now we try to find whether any number can satisfy the solutions. We start with 1, let's say 1. So x3, t is 1, right? T is 1. So if t is 1, x3 is 1. x2, 2 minus 1 will be 1. x1 equals to 6 minus 2, 1. Remember, t is 1. So it will become 4. Insert these 3 into the equations. We try with the first one. x1 is 4 plus 2 x3, which is 1, equals to 6. True. Start with number 2. x2 is 1 plus x3 is also 1, equals to 2. Correct. So number 1 here satisfies this equation. Let's try with 3. t is 3. So for x3 it will be 3 because it's the same. x2, 2 minus 3, it will be negative 1. x1, 6 minus 2 multiplied by 3 also will be 6. It will become 0. Now let's test these numbers. So for the first equation, x1 is 0 plus 2x3, 3. So we get 6, right? So this is correct. Number 2, x2 is negative 1 plus x3, which is 3. So it is true. Negative 1 plus 3 is 2, right? So this also satisfies. T equals to 3 also satisfies this solution. So it will have many solutions. 1, 3, any number you put also can have a solutions. Okay, for number 3, for no solutions. We have two linear equation, x plus y equals to 2 and x plus y equals to 4. If you plot this into the graph, you will get these two lines, 4 and 2, for x plus y equals to 4, for x plus y equals to 2. So if you see, there is no parallel between these two linear equations. So there's no points between these two equations. It is parallel lines. So there is no solution and it is inconsistent. Okay, example for no solutions. We have two linear equations. 3x1 plus x2 equals to 5, 3x1 plus x2 equals to 7. As you can see, if you put any number inside here, it will not satisfy both. It will not satisfy because this one is the same, right? 3x1 plus x2, but it's equal to 5. This one is equal to 7. Of course, any number cannot satisfy both. So these two lines are parallel and do not intersect with each other. So it is inconsistent, sorry. Now we come to matrices. I think you guys are familiar with matrix. Okay, what is matrix? It is a rectangular array of number, and the number themselves are called entries of the matrix. Matrices are usually denoted by uppercase letter A, B, C, D, like this. A, B, B, C, D. And this is the type of matrix that we have. As I mentioned, matrices come in various rectangular shapes depending on the number of rows and column. A matrix with m rows and n columns is said to have size m multiply n. So the rows come first and then the columns. So this is 2 rows, right? 3 columns. So 2 plus 2 multiplied 3 columns. And 3 column will be same thing, 3 and 3. 3 rows for the first one, rows, and this one is column. A matrix size of 1 multiply n is called a row matrix. This is the example. We have 1 row but no columns. A matrix size of m multiply 1 is called a column matrix, whereby we have this one, 1, 4. It's a column-based matrix. A matrix with equal numbers of rows and columns is called a square matrix, where we have 3 rows, 3 columns, 2 rows, 2 columns, 4 rows, 4 columns. It is a square matrix. How to find the determinants of matrix A? For example, this is a 2 by 2 matrix, and to find the determinants, we will use these equations. But for the 1 by 1 matrix, the determinants will be the only matrix inside the matrix A. This example asks us to compute the determinant of matrix A. So as I mentioned before, we need to make it like A D minus B C. So this is A, this is D, this is B, this is C. So it will be 2, 4 minus 1, C is 5. Alright, and then you will get a solution. 2 multiply 4, 1 multiply 5. Solution is 3. For any square matrix A, you must find the submatrix, and it can be formed by deleting the ith row and jth column of A. For example, this one is used for 3 by 3, 4 by 4, larger than 2. Okay, let's say 3 by 3, 4 by 4. Then you need to use this submatrix methods. Okay, for example, this one is 3 by 3. If you want to find the determinant of A12, so this one is row, 1 is row, 2 is column. So you must deselect the first row and the second column. And these 4 numbers will be your determinants here, in order for you to calculate the determinants for A12. For n more equals to 2, the determinant of this type of matrix, let's say 2, 2, 3 multiplied by 3, 4 multiplied by 4 matrix A, is the sum of n terms of the form of plus minus A. I will explain later how to add plus and minus signs. We have plus and minus signs, okay? Alternating means that plus and then minus, plus and then minus. I will show this later. Where the entries of A11, A12 and so on are from the first row of A. Okay? It's okay if you don't understand, we will go to the example later. This is the equations. We also need to know about the cofactors. This we use in later examples where we need to calculate the cofactors. And then these cofactors can be used to find also the determinant of A. For example here, A11 multiplied by cofactor 11, and then plus A12 multiplied by cofactor A12. Alright, we will use this equation later. This is the plus minus signs that I mentioned before. It is alternating between each other. If you can see, let's say you have 3 by 3 matrix, which will be this one, 3 by 3 matrix, right? This one. So the first column here, the first row in the first column should be positive, and then followed by negative and positive. The second row start with negative, positive, and then negative. The third row, you repeat again the first row, positive, negative, positive. Okay, this is the plus or minus signs in the cofactor that depends on the positions. So it depends on the position where it belongs in the matrix. The determinant of the matrix can be computed by a cofactor expansion across any row or down any column, which means that sometimes the question can ask you find the determinant of matrix A across the first row. So you will calculate for the first row or any columns, meaning that they can ask you find determinant in the second row. Okay, it depends on the questions. So this is the expansions across the ith row using the cofactor. So if they ask you to find for the row, this is what you use. If they ask you to find the cofactor expansion down the column, this is what you use. We will see in the example later. Okay, as I mentioned, this example asks to find determinant of a 3 by 3 matrix, using the first row expansions. So using the first row expansions. So where is the first row? This is the first row, right? So find the determinants of this matrix using expansion of the first row. So determinant A is equals to A11. Why 11? This is the first row. And then minus, remember, plus, minus, plus, minus, plus, minus, plus, minus, plus. Alright, so this one minus A12, this one 12, and plus A13. How we get this? We get this by for A11, this is the this is where you get it. Let's say for A12, this is where you get it. For A13, this is where you get it. Okay, this is another example, but this time they ask you to use a cofactor expansion across the third row. So across this row, the third row, to compute determinants A. So remember, this is the plus minus sign, this is the plus minus plus. Okay, so this is the first number, the 3 1, because the third row first column is 0, -2, 0. And then how you get this value is for 0, as I mentioned, 5 4 0 -1, and you do the same for these two. And remember how to calculate this, AD minus BC. Then after you calculate, you will get this answer. Alright, we have an exercise for you guys. I have two questions, both are 3 by 3 matrix. Compute the determinants of these matrices using cofactor expansion. For the first one, using the third row. For the second one here, the B, using the first column. I need you guys to do this, and I will ask you in my next class. Metric inverses. I think you guys are familiar with metric inverses already. If A is a square matrix, a matrix C is called an inverse of A if it satisfies both of these equations. So C is equals to A inverse. How to find metric inverses? Okay, if matrix A equals to AB, this 2 by 2 matrix, and AD minus BC is not equals to 0, means you have a value 1, 2, whatever value you have, value not 0, the A inverse is equals to 1 divided by AD minus BC, and then you must multiply with this matrix. A become here, D becomes here, and B and C both have the negative signs. AD minus BC is the determinant of A and also is the adjoint of A. Okay, examples. Find the inverse of matrix A, which is a 2 by 2 matrix. Now, as I mentioned before, you must have one AD minus BC. So AD is 4, 2 minus B is 1, 3. And then you also must have D over here, 2, A here, 4, B and C is still the same, but now they will have an inverse, negative signs. Alright, so you should have this, and after you calculate, you will have this value. This is the A inverse. How to check whether this A inverse is the correct answer for your matrix A? You can make a calculation for 1, multiply by the first row, and then you will get 1, multiply the first row, and then same for 1 multiplied by the second row, you will get 0. the second column, the second row, 3, 2 multiplied by the second row multiplied by the first column, you will get 0. And the second row multiplied by the second column, you will get 1. Try this out. If you will get 1, 0, 0, 1, then this shows that this is the correct A inverse for the matrix A. Before this, the example calculates matrix inverses for 2 by 2 matrices. Now, how to compute the matrices of 3 by 3, 4 by 4 or more? 3 by 3 especially here. For this example, they ask you to calculate the inverse 3 by 3 using cofactor matrix, which is the A inverse will equals to the 1 divided by A, which is the adjoint A, equals to also a cofactor matrix of A transpose. What it means, we'll see the example. Okay, now we have a 3 by 3 matrices. The first step is to find the determinants of A. So remember the step that we used to find the determinants. Let's say for the first row, we have 2, 1, 2. So this is a plus, this is a minus sign, this is a plus sign. Alright, and then we find the value. Let's say for this number 2, this is the value. And then do the same for the second one and the third one. When you get that, when you get this, do the calculation AD minus BC. Then you will get this value. And at the end, you will find your determinant of A. This is the first step. Then the second step, we need to find the cofactor matrix A using these equations. Okay, let's start with the determinant A11. You need to calculate the determinant for A11. This is A11, right? A11. So you will get this value. When you do calculation, you will get 1. For the second one, A12, you will get this value, and with the calculation, you get 2. And then repeat the process for A13. You get this value, you do the calculations, you will get this one. The calculation is AD minus BC. Okay. After you get your answer, use this equation, insert your answer into these equations. For example, A11. So this is negative 1. I is 1 plus J is 1. Determinant A, we already calculated here, is 1. So multiply by 1. So negative 1 power of 2 will be 1 power of 2 is 1. 1 multiplied by 1 is equal to 1. So this number, you put it here. Okay. Let's look at the second one. We have A12. So negative 1, 1 plus 2. Determinant A12 is 2. So multiply by 2. So negative 1 power of 3. Is equals to negative 1 multiply 2. It will be negative 2. So this number you put inside here. Okay, and then the last one, is A13. A13, is -1, the I is 1 plus 3 multiplied by -1. This one, A13, the determinant of A13. So -1 power of 4. 1 multiply -1. So it will be, okay, then use the same thing that we do on the first row to the second row, okay, whereby you need to find the determinants of A21, A22 and A23, get the answer for the determinants, and then use this cofactor -1. Let's say for the 21 here, 2 plus 1, determinant of 21 is -3. So the answer will be -1 power of 3 will be -1, -3 will be 3. So this 3 will be the first one. And do the same for these two rows. These two value here, -8 and 1, find it from here. Again, do the same thing for the third row, whereby you will find the determinants and insert the determinants inside this equation. Then you can find the cofactor matrix for the third row. The next step is to transpose the cofactor matrix that you found. Transpose is how you change your from the adjoint here 1 to 131 to the column to rows. Okay, for second column, second rows, and the third columns to the third rows. This is how you transpose. I think you're already familiar with this. Okay, and the last step is use this equation. For A inverse, we have 1. Where we get this value? We get this value from the first slide we calculate the determinants, which is -2. You can go back to the first slide of this example, where we calculate the determinants and we find the value of -2. So we put the value inside here, -2, and this is our adjoint A, where we already transpose it here. So we put it this one. So it's equals to, you multiply for each value inside the matrices. Okay, then you get this value as the final value, final answer. Okay, I will give you exercise for these matrices. Find the inverse of the given matrices. One is the 3 by 3 and one is 2 by 2. I will ask this in your next class, and you need to answer to me, and we will check it together. As I mentioned before, system of linear equations is a finite collection of linear equations, and it is a system of m equations in n variables, like this one. Okay, we have a matrix form of system of linear equations represented by Ax equals to b. This is the A, this is the x, and equals to b. A is the matrix of coefficients, x is the matrix of variables, and b is the matrix of constants. Then we also have what we call as augmented matrix, where this is the symbol. Okay, if you see things like this, the matrices like this, it is called as an augmented matrix. Okay, how to convert from the form matrix to the augmented matrix? This is the example. So they give you a system. We have x1, x2, and x3. And for Ax equal to B, if you have no numbers here, x1 and x2, it is 1. So 1, 1, 5, 3, 2, -1. Remember this 1, so 1, 2, -4, plus 1. You remove the x1, x2, x3, x1 to the first one, x2 followed by x3 equals to the B, 5, 10, and 8. This is the form. For the augmented, same thing. We get the A, 1, 1, 5, 3, 2, 1, 2, 4, 1 here inside the matrix, and then we just input the B, which is the 5, 10, and 8. There's no need for an X, the variables. No need for variables in the augmented form, the augmented matrices, sorry. Row echelon matrices. A matrix can be said to be row echelon form if the following conditions are satisfied. Remember, these conditions must be satisfied in order for them to be called row echelon matrices. All zero rows, if any, means that there are possibility that there are no all zero rows. If they are, they must be at the bottom of the matrix. If two successive rows are non-zero, the second row starts with more zero than the first. So, if two successive rows are non-zero, the second row starts with more zero than the first. You must have more zero from the first one, moving from left to right. As I mentioned in the previous slide, every row with all zero entries is below every row with non-zero entries. Means that this one, all zero, must be at the lowest in the matrix. Each leading entry of a row is in a column to the right of the leading entry of the row above it. So leading entry, any non-zero value. If you see here in the matrices, this is the leading entry. And each leading entry of the row is in the column to the right. Means that this is the leading entry, and then 0, 0, this is the leading entry of the row, the number, and then continue by this one, all to the right. The first one, the second one to the right of the first one, the third one is to the right of the second one. It must be like that. The second row, let's say this statement here, the second row starts with more zero than the first, left to right. So you must have 0, 0 first, then the leading entry. The third conditions, all entries in the column below a leading entry are zeros. This one, leading entry, all of it are 0. This one is leading entry of the second row, under it all 0. The third row leading entry, all 0. So we have three main conditions. If all 0 in the row must be the lowest one, then if leading entry must be on the right of the previous row, this is the first row, second row leading entry, third row leading entry, all on the right. And then under the leading row, the leading entry, the column under it must be 0. Then it will be called as the low echelon form. We also have what we call as a reduced row echelon form. For reduced row echelon form, we have two extra conditions. The first one is the leading leftmost non-zero entry in each non-zero row is 1. So it cannot be any other number. The leading entry must be 1. 1, 0, 0, 0, 1, 0, 0, 0, 1. So the leading entry for the first row is 1. Leading entry for the second row is 1. Leading entry for the third row is 1. Each leading one is the only non-zero entry in this column. So if you see in this column, this is the leading one is the only non-zero. The leading one is only non-zero. The leading one is only non-zero. So this is what we call as reduced row echelon form. Reduced row echelon matrices, sorry. Example. This example show that these two matrices is in a row echelon form. If you can see, it satisfies the first one. If you have all zero, it must be at the lowest one. And then all the entries, the leading entries, must be to the right. This one, the first row, the second row is to the right. Same as this, all 0, and then the leading entry all to the right, each row 3, and then the second row to the right of 3, the third row to the right of 2, number 1 here. And then under 2 all is 0, and under the leading for row 2 also 0. Under 3 the column is 0, under 2 here the leading one is 0, under 1 also is 0. So it is a row echelon form. This one also a reduced row echelon form. Why? Because it satisfies all the row echelon form, whereby all 0 is the last one, and then if any means this one have it. So the leading entry to the right, and under it is 0, under it is 0, under it is 0. But for reduced conditions, the leading entry must be 1. So this is 1, this is 1, leading entry also 1, 1, 1, and inside the column itself, it is the only number that is not 0. Means that looking up, also they are the only one. Looking up, also they are the only one. Looking up, also they are the only one. So this is a reduced row echelon form. This example are not in reduced row echelon form or row echelon form at all. Let's see this one. This one they have 0, 0, 0, but it is not at the lowest one, so it does not satisfy directly. For this one, as you can see, the leading entry, this is number 1 here. This is the first row, the leading entry. The second row, okay, the leading entry is to the right, but the third row, the leading entry is the same as the leading entry, same position as same column as the leading entry of the second row. So this does not satisfy the row echelon form. If it does not satisfy row echelon form, of course it will not satisfy the reduced row echelon form.